Hello, this is a short introductory talk on our paper, A Characterization of 3D Steady Euler Flows using Commuting Zero-flux Homologies. So this is a paper by Daniel Peralta-Salas, Anna Rechtman, and myself, which was recently published in Ergodic Theory and Dynamical Systems, and they kindly asked us to make this short introductory video. So let me begin by explaining what is a steady Euler flow. So we have a fluid in a Riemannian 3 manifold. This fluid is invested, meaning it has no viscosity, and incompressible, meaning that the density is constant, and we take it to be equal to 1. So the motion of this fluid is described by the Euler equations, which appear here. So here U is the velocity field of the fluid. This is a time-dependent vector field on the 3 manifold. And P is the inner pressure of the fluid, which is a scalar function, which depends not locally on the velocity field U. So the first equation here is just conservation of momentum, Newton's second law. And the second equation is the conservation of mass, or equivalently, the conservation of volume, because density is constant. So if the solution U does not depend on time, so this term is 0, we say that the solution to these equations is a steady or a stationary Euler flow, and it is modeling a fluid flow in equilibrium. So in that case, the equations can be rewritten in the following manner. So you have that U, a vector product with its curl, must be the gradient of function. This function is called the Bernoulli function. And the curl of the velocity field here is often called the vorticity field of the fluid. So it is often useful to consider these equations not in the tangent bundle, but in the cotangent bundle of the manifold. So for that, we introduce a one-form alpha, which is the dual of the vector field U by the duality between one-forms and vector fields defined by the metric, by the Riemannian metric G. And then this equation here becomes this equation. So if you put the velocity field U in the two-form d alpha, then this must be an exact one form, okay? Minus dB, where B is again the Bernoulli function. Okay? And then you still have the divergence free, or the volume preserving condition. So here the two-form d alpha is also called the vorticity two-form of the fluid. So now if you take the exterior derivative of this equation, what you get is that the Lie derivative of the two-form d alpha, or the Lie derivative of the vorticity along the velocity is 0. Or say differently, the vorticity two-form d alpha is preserved by the flow of the velocity field U. So this is known by the name of Helmholtz transport of vorticity. Vorticity is transported by the flow. Now we can introduce the main notion of this talk, which is the concept of Eulerizable flow. So we say that a volume-preserving vector field on a manifold is Eulerizable if it is a solution of the steady Euler equations for some Riemannian metric on the manifold. So notice here that even if it's not apparent, the Riemannian metric it's in the Euler equation, so it's necessary to even define the Euler equations, because this one form alpha must be the dual of the velocity field U. So the question is, if given U, you can find some metric so that the dual of U satisfies this. And here notice also, this is important to emphasize, that the second Euler equation, the divergence of U, does not involve that does not involve the metric. You can define the divergence without the metric, just with the volume form. This is just saying that U is volume preserving. Okay, so here is a straightforward observation. If you have a volume preserving vector field U, which is non-vanishing, it is Eulerizable, so there is a Riemannian metric that makes it into a solution of the steady Euler equations. If and only if there is a one form alpha that is positive on the vector field, and such that U d alpha is an exact one form. And this is easy to check, because the moment you have this, in particular, this equation is already satisfied for the one form alpha, and the fact that alpha is positive on U means that you can easily construct a Riemannian metric that so that alpha and U are actually dual of each other for this Riemannian metric, which is the condition that was left once you had this. So this is a trivial observation, but what we are after really is a more dynamical or topological characterization of Eulerizable flows. And more precisely, we would really want to have some abstractions on the dynamics that can be present on an Eulerizable flow. So for example, we could ask, are there some arrangements of flow lines, some dynamics that cannot be present in an Eulerizable flow? So if we see them in a flow, we already can say that it's not going to be Eulerizable. So there is no chance of finding a metric that makes it a solution of a steady Euler. Or in particular, maybe the opposite is true. So maybe there is no such obstruction, and in principle, any volume preserving vector field could be homomorphic to an horizontal flow. So we are going to see that that's not the case. So our characterization is going to be inspired by Sullivan's characterization of geodesible vector field. So let me recall what is a geodesible vector field. So it is a vector field whose orbits are all geodesics for some Riemannian metric on the manifold where the vector field is defined. So Sullivan proved that an unvanishing vector field on a compact manifold is geodesible if and only if these two sets of, we are going to see, of generalized loops associated to the vector field do not intersect, or rather intersect trivially. So what are these two sets? So here these are going to be sets of one currents, by the way. And let me give an intuitive idea of what they are. So to form the set Bx, you take the boundaries of surfaces which are tangent to x. Okay, so this is a set of loops, of closed curves. And now these closed curves, you can consider them as linear functions on the space of smooth one forms, right? Because you can integrate a one form against a closed curve, and this gives you a linear function on the space of one form, a continuous linear function on the space of one form with respect to the smooth topology. Okay, so now you can take linear combinations of these linear functions to get other linear functions, and you can also take the weak star limit of these linear combinations, and then you get an object against which you can still integrate smooth one forms, but that is no longer it is no longer a geometric loop, but we could call it a generalized loop. Okay, so it's like a boundary of a generalized surface tangent to x, or two chain rather, because you are taking combinations of those. Okay? Combinations with positive and negative coefficients, by the way. So this set here is a linear subspace of the space of one currents, of the space of continuous linear functionals on the space of one forms. Okay. So the set Cx, calligraphic Cx, is the set of foliation cycles of the vector field x. So what is a foliation cycle? The simplest example of a foliation cycle is a periodic orbit of the vector field. So this is a loop, okay, that is tangent, closed loop, which is tangent to the vector field x. But more generally, a foliation cycle can be defined as follows. So you take an orbit of the vector field that is not periodic, it does not close. You follow it for a certain amount of time, and then you can always close it with a little segment. This is no longer tangent to the vector field, of course, but then you still get a linear function on the space of one forms that integrates exact one forms to zero, so that is closed. Okay, and now you can repeat this process. You can take this orbit for longer and longer times, and if you normalize, if you divide by the time, you get a sequence of loops. Okay, and in the limit, when the time goes to infinity, you still get an object against which you can integrate one forms, and which integrates exact one forms to zero. And this object is a foliation cycle. So it's, in some sense, a generalized periodic orbit of the vector field x. And actually, you can show that these objects are in one-to-one correspondence to the invariant measures of the vector field x. Okay. So we can call them generalized periodic orbits. So Sullivan's characterization is saying that a generalized periodic orbit cannot be the boundary of a generalized tangent surface. So we are going to give a similar characterization based on the following observation. So if you have an Eulerizable flow on a three-manifold, then these are 2 points to consider. The vorticity W commutes the velocity field, so they would commute. And also, second observation is that by Stokes' theorem, if the circulation of the velocity field along some loop is positive, then the flux of the vorticity field through a surface bounding this loop must be also positive. In particular, it cannot be zero. So this motivates the introduction of the following space of generalized loops. We're going to introduce the set F sub x associated to the vector field x, which is the set of boundaries of surfaces through which the vector field x has zero flux. Okay, so we are going to call these zero flux, boundaries of zero flux surfaces of x. And then still these define linear functions on the space of smooth one forms, and we can take weak star limits of these linear functions. And in general, we will get the set calligraphic fx closed. So taking the weak closure. This is going to be a linear, this is very important, a linear subspace of the space of one currents. So the main theorem says the following. If you have a non-vanishing volume preserving vector field on a compact three-manifold with trivial first homology group, so we are going to see that this is going to be necessary in the proof, then U is Eulerizable if and only if there is a non-trivial vector field omega that, first of all, commutes with U, and second, the set of generalized periodic orbits of U, so the set of Fourier cycles of U, does not intersect, so a generalized periodic orbit cannot be the boundary of a generalized zero-flux surface. So these two sets of one currents intersect only in the zero one current. So we are going to see that the direct implication, the fact that if you assume that U is irreducible, then this happens, this intersection is trivial. It's easy to show following this observation. So the one that is more involved is the converse implication. So if you have this, that this intersection is trivial, then U is irreducible. That is, then you can find the metric. So let's see how that converse implication is proven. Here the key is to use the Hahn-Banach theorem. So let me first put the whole proof here so that you can pause the video if you want to see it in a bit more detail. I'm going to be very brief. So the crucial idea is that the set of Fourier cycles, so this CU, is a cone in the linear space of one current. It is a cone with a compact convex base that we are going to call K. Okay. So in particular, if the cone only intersects this linear subspace, so the space of boundaries of zero-flux surfaces in zero, it means that it intersects this compact convex base of the cone. It doesn't intersect this set. So the intersection between this compact convex set and this linear subspace is empty. So this is calling for an application of the Hahn-Banach theorem, because then you can find this intersection is empty. You can find a linear function in the space of one currents, in this space of generalized loops, that is zero here in this linear subspace, and that is positive here in this compact convex set. But now this is the second crucial observation. A continuous function on the space of one currents is again a smooth one forms, because smooth one forms and one currents are dual to each other. Okay. So this means that this functional gives rise to a one form alpha, and the fact that the functional is positive here, one can show that is equivalent to saying that alpha is positive on the vector field U. Okay. And the fact that the linear function is zero here in this linear subspace can be shown to be equivalent together with the fact that U and W commute. This is equivalent to the fact that this one form U d alpha is closed. And then, since we are assuming that the first commutative group is zero, this means that U d alpha is exact. So to sum up, we have actually found a one form alpha which is positive on U, and such that U d alpha is exact. So we can construct now the metric that makes alpha a dual of U, and we have shown that U is irreducible. I'll give now an application of this characterization, which is that Euler flows cannot have plugs. What is a plug? A plug is a cylinder with a vector field together with a vector field with an interesting dynamics inside. So the point is that by the local flow box theorem, any vector field away from the zeros can be written in appropriate coordinates, in local coordinates, as the vertical vector field on a cylinder. And the idea of a plug is to modify in the interior of the cylinder these vertical dynamics so that something interesting happens, and you can locally change the dynamics of vector fields for applications like destroying periodic orbits or introducing new invariant sets, etc. So more precisely, a plug is a cylinder together with a vector field X with the following dynamics. So the vector field is still the vertical field on the boundary of the cylinder. It's transverse to the top cap and to the bottom cap, and it's tangent to the size of the cylinder. But the key is that there is at least one orbit that does not exit the cylinder. So for some point in the bottom cap, its orbit remains always trapped inside the cylinder for all that positive time. And then the third condition is that if a point in the bottom cap, if the orbit of a point in the bottom cap exists, then this orbit exits by the opposite point Q1. So an example of an infinitely smooth plug, which is compatible with being volume preserving, so you can make the dynamics still preserve any volume inside it. It's a Wilson plug, which introduces a ring invariant cylinder in the dynamics. So I'm going to show a picture. Here you see that the vector field is still the vertical field on the boundary of the cylinder. It's entering here, and most of the orbits exit here, some of them. Okay? But then you have two, instead of being the vertical vector field inside, you have two orbits here, two periodic orbits here. And what happens is that some orbits that start in the bottom, they get attracted by these periodic orbits here. So there is a cylinder here of a circle of orbits that have this periodic orbit as limit cycle. Okay? And then the same happens, but in the backwards in time for the orbits in the top cap. Okay? So here, if you go backwards in time for some circle of starting initial conditions, you have this orbit as limit cycle. And in the middle, you have that points that start here near this bottom orbit, they get attracted towards the top orbit. So the key is that anytime you have such a dynamics, or more generally, a more general Planck dynamics with a trapped orbit, what happens is that you are creating a foliation cycle, which is the boundary of a generalized zero-flux surface of the vorticity. Okay, so that's why you cannot have Planck. So what we do to show this is that first you use Sullivan theorem to show that geodesible flows cannot have Planck, and then you assume that U is irreducible and non-geodesible. You assume it has a Planck, and you get a contradiction, because you get that the moment you have a Planck, some foliation cycle that is some generalized periodic orbit is the boundary of a generalized zero-flux surface of the curl of the vector field. Okay. So this contradicts our characterization, and the theorem follows. Euler flows cannot have Planck. So this is the end. Thank you very much. I hope that this short talk has encouraged you to have a closer look at the paper.